August 2003. Summer demand for electricity is peaking. In a rural corner of Ohio, a high-voltage transmission line carrying heavy current heats up. The metal expands, and the wire sags downward until it brushes against the leaves of an overgrown tree branch. Under normal circumstances, this physical short circuit triggers a local relay. The system isolates the damaged section. Nearby customers might see a flicker, and repair crews get dispatched. Instead, that single brush with a tree branch initiated a chain reaction that disconnected 50 million people across the northeastern US and Canada. Subways halted mid-tunnel, water pumps stopped, hundreds of thousands of commuters were stranded, and thousands were forced to sleep on the sidewalks of New York City. The question is, how does a highly localized, perfectly routine physical fault escalate into a continent-wide collapse? To understand the collapse, we have to discard the most common misconception about the power grid. It is not a giant battery. There is virtually no storage capacity holding power in reserve. This animated scale illustrates a rigid mathematical requirement of the grid. Every single watt of energy consumed must be generated in that exact same millisecond. This perfect balance maintains the system frequency, usually 60 Hz in the US or 50 in Europe. Break that balance and the grid stops functioning as a unified machine. It instantly becomes a highly volatile series of falling dominoes. Because there is no storage buffer to absorb errors, any physical disruption to the system has to be managed in milliseconds. The electricity powering the grid comes from thousands of massive, rotating machines. These synchronous generators weigh hundreds of tons and spin constantly. Look at this map of the grid. Because they are connected to the same network, these machines must rotate in perfect mathematical lockstep across vast distances. This coupling means a voltage drop in Ohio is immediately felt by generators hundreds of miles away. Which brings us back to that tree branch in 2003. Pushing heavy current through a transmission line creates resistance, which generates heat. That heat caused the wire to expand and sag into the tree, creating a massive fault. Local protective relays did exactly what they were designed to do. They tripped the circuit breakers to sever the connection and save the wire. But the raw electrical power flowing through that corridor didn't just disappear. On this network map, stranded power instantly seeks the path of least impedance, surging into adjacent, thinner lines. Carrying triple their normal load, these lines overheat and sag. As they fault and trip, power is forced onto an ever-shrinking number of surviving cables. As massive transmission corridors failed in rapid succession, the delicate balance of the grid was shattered. System voltage and frequency began to swing wildly across the entire continent. Those massive synchronous generators instantly detected these extreme frequency swings. To prevent their physical axles from literally tearing themselves apart under the mechanical stress, the power plants automatically disconnected from the grid. The entire region collapsed precisely because every individual grid component successfully executed its own local protection protocol. Today, grid operators employ a hidden world of advanced defense systems. They use out-of-step relays and automated sensors to track the grid's frequency heartbeat in real time, trying to catch these massive power swings before they escalate. But when a cascade is accelerating and those initial blockades fail, operators face a brutal physics problem. How do you stop a collapse that is already in motion? The ultimate fail-safe is an automated protocol known as low-frequency demand disconnection. As we see on this graph, tracking system frequency plummeting toward the danger zone, this protocol deliberately severs power to entire communities to arrest the fall. It is cold, mathematical triage. Operators must artificially destroy electricity demand to match the suddenly reduced supply. They sacrifice a limb to save the body. So the next time the lights unexpectedly go out in your neighborhood on an otherwise calm night, it may not be a localized failure. You might be experiencing the visible artifact of an entire interconnected system fighting to survive. In the control room, the choice is never between keeping everyone online versus turning a few people off. The choice is losing a few power lines right now or losing the entire continent in a matter of minutes.